All right, so now we're up to our second type of intermolecular bonding. We're moving on to polarity. Now, this one does not go away. You will be learning about polar molecules from now until the end of the time that you decide to finish learning chemistry. They are super important. They even come into play if you're doing biology. We talk about them specifically when we talk about what molecules can pass across the cell membrane. And so it's a really valid and really important concept that we get knuckled down into in chemistry. So we're still on the same dot point. So we're talking about an explanation of polar and non-polar character. So we're going to go through our notes, and it says just below the heading polar and non-polar molecules, you get this table here. It shows you the group 15 hydrides. So that is anything that's in group 15 bonded with hydrogen. And it shows you the group 16 hydrides. So anything that's in group 16 bonded with hydrogen as well. Okay, so it would be NH3, yeah, because N has 3 bonding electrons left, and so it would bond with 3 hydrogens. And what do you notice? That they have very low melting points. And then the group 16 hydrides, you do the same. So let's have a look at the paragraph underneath it. Looking at the hydrides down a group, the melting points don't really follow the order of their relative molecular masses. You have some light molecules, okay, that have higher melting points than some heavy or large molecules. So have a look at this NH3 here. This NH3 here has got a higher melting point than both of these. So that's a bit weird. It's smaller. It doesn't have as large an MR. The same goes with this one. Have a look at water. It has a higher boiling point than all of these. Okay, and that doesn't follow our pattern. If you think about the examples we were talking about just before, definitely not. Yeah, water is weird. This ammonia is weird. So why does it happen? Clearly, mass and size of the molecule is not the only factor that affects its melting point. So that brings us to our next topic, polarity and polar bonds. Okay. When two different, so I'm going to go through your paragraph first. When two different non-metal atoms form a covalent bond, one atom usually attracts bonding electrons more strongly than the other atom. So in the hydrogen chloride molecule that we're looking at here, the chlorine atom, yeah, over here, attracts the bonding electrons, more strongly, okay, than the hydrogen atom. This is because chlorine, and we're going to go back to what we did in area of study 1, chlorine has a higher electronegativity. The chlorine atom has a higher electronegativity than hydrogen. This means that the bonding electrons are going to spend more time closer to the chlorine than to the hydrogen atom. Yeah, remember electronegativity. What does it mean? Electroattraction. So the electrons in this molecule are going to spend more time closer to the chlorine than they will to the hydrogen. And you can't see anything that I'm looking at, which is great. So let's share it one more time, just to make sure that we get what I'm looking at here. Sorry, girls. Keep my annotations. Let's play it one more time. All right, I've probably just shrunk. So this is what I was writing here. You can see here is a picture of hydrogen chloride. You can see on the right, we have that the hydrogen chloride attracts the bonding electrons more strongly. And this is because it has an increased electronegativity. What that means is that the chlorine end of this molecule is always slightly more negative. Because of this difference in electronegativity, that means this end is always going to be more attracted to the electrons are always going to be more attracted to it, so it's always going to have an overall negative charge. So this is different to dispersion forces, where one side of the molecule develops negative charge and then the next side of the molecule develops it, and they keep switching between the two. In this case, it's what we call a permanent dipole. Okay, so finishing off that paragraph, it means that the bonding electrons spend more time closer to the chlorine than the hydrogen atom. The chlorine end of the molecule becomes slightly negative and the hydrogen end becomes slightly positive. The chlorine atom has a partial, not a whole, negative charge associated with it, and the hydrogen atom has a partial positive charge. So that's what this little kind of weird delta symbol here is referring to. It's referring to the charge. So there's a little bit of positive charge on this side and a little bit of negative charge on the side of the chlorine. So over the page it says the bond within the hydrogen chloride molecule is said to be called a polar covalent bond. Okay, so what that means is this polar covalent bond within here. So here is the polar covalent bond on this picture. That's due to the differences in electronegativity. This molecule of hydrogen chloride is said to be polar. We can call the molecule a polar molecule because there's a net buildup at charge at either end, and this is a permanent dipole, okay, equals permanent. So we had an instantaneous dipole. This time we've now got a permanent dipole. All right, so just underneath this picture that we're looking at here, this type of intermolecular force of attraction, we call this dipole-dipole attraction. So this is between two polar molecules. We call that a dipole-dipole attraction. What other forces have they got in play here? Okay, so you've got dipole-dipole attraction, plus you've also got dispersion forces. So there's always dispersion forces. Remember, always, always dispersion forces. So unless the molecule is very big, this type of intermolecular bonding is stronger than dispersion forces. So a permanent dipole or a polar bond, or this dipole-dipole attraction, that is a stronger bond than dispersion forces. Stronger than dispersion forces. All right, it says down the bottom here, all right, note, the greater the difference in electronegativities between the atoms of the molecule, the stronger, or the greater the buildup of charge at each end, and so therefore the more polar. So if you look at two atoms and they are within a molecule and there's only a slight difference in their electronegativity, it's kind of weakly polar or not very polar, but it is still polar. If you look at them and they've got a big difference in their electronegativity, then you say that that is a very polar, or it's more polar molecule. So the more polar a molecule is, the stronger that dipole-dipole attraction is. And that makes sense. Yeah, if you've got a larger buildup of negative charge on one atom and positive on the other, they're going to be more attracted to their neighboring molecules. Now, very important, both dipole-dipole and dispersion forces, much, much weaker than covalent. Okay, so the last bit is how can you tell? Yeah, so when considering if a molecule is going to have a permanent dipole, you need to look at two things. And this is what we're going to do in our next videos. We're going to be identifying whether or not we think a molecule has got dipole-dipole bonding or just dispersion forces. So to begin with, there has to be a difference in electronegativity between the atoms. So this means that we're not talking about H2, yeah? Because they have the same electronegativity between the two atoms. Yeah, so that one's not going to work. So what we are talking about is something like HCl, because there is a difference in electronegativity. Now, the other thing we look for here is it's not just about the difference, but it must also plus, 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 the molecule needs to be asymmetrical. Do you know what asymmetry is? Asymmetry is where one side is different to the other. So at the moment, my hair is asymmetrical. This side here has got kind of no part in it. And then if I cut myself down this side, you can see that this side of my head has got a part in it. So this side of my head and this side of my head are different. So therefore, my hair is asymmetrical. Okay, and hopefully that helps us out. We're going to do some practice in our next video.